So the solubility product constant. So we all actually have some kind of background knowledge when it comes to solubility. You've all probably at some point in your life taken some sodium chloride, put it into water, and watched it dissolve. And after it dissolves, you add more, that dissolves, you add some more, you have to stir it a little bit, it dissolves. But at some point, there is no more salt that you can dissolve into the solution. And at that point, your solution is said to be saturated. So a saturated solution is just going to be a solution containing the maximum concentration of solute dissolved in the solvent. So solute being your salt and solvent being the water. So before you actually couldn't dissolve anymore, you were in an unsaturated solution, which is just a solution that does not have the maximum concentration of dissolved solute in solvent. Now, the next two definitions, KSP and QSP, is what we're going to spend a little bit of time on. And the definitions are, for KSP, the equilibrium that exists between a solid and its dissolved ions in solution. Great. QSP, the solubility product of the concentration of ions in solution of a dissolving ionic solid. That is a little bit to take in. All right, so now to explain QSP and KSP, we're just going to look at a solution of water as we dissolve sodium chloride in it. So right now, we just have a liter of pure water, and I'm going to start to put some solid NaCl in it. So before I dissolve the NaCl, I have this structure in the solid. So I have Na bound to a Cl, but when I take it and I put it into solution, it's going to dissolve into Na plus and Cl minus ions. So let's say I have a large sample of sodium chloride. So here we go. Here is a sample of sodium chloride. Each one of these red dots represents Cl. Each one of the green dots represents Na, and they are all bound to each other. They haven't dissociated yet because I haven't put them in the water. But what's going to happen when I do put this into the water? Well, this sample is automatically going to start to dissociate. So some of these particles are going to break into Na plus ions and Cl minus ions. So for every one of my NaCl solids, when it dissociates, it'll produce an Na plus and a Cl minus. So I'll have one Na plus and then one Cl minus. And when I first put this sample in, it's going to dissolve, 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 and it's going to keep dissolving until I suddenly can't dissolve anymore. And when I can't dissolve anymore, something interesting happens. At that point, when I can't dissolve any more sodium chloride, I'm going to be at the equilibrium point. And so let me just write real fast. Too big. At saturation point, there is an equilibrium. But what is the equilibrium? What's at equilibrium? Well, let's say when I do dissolve NaCl into water, and I have so much salt that some doesn't dissolve. That salt that's sitting there isn't just sitting there unreactive. That salt is actually still dissociating into the water. But what's interesting is that for every single particle that you dissolve into the water, one Na plus and one Cl minus is going to precipitate out of the water. So at the equilibrium point, I'm at my saturation point. I have the max number of ions that this solution wants to have. For every one that continues to come out, one Na plus and one Cl minus that has dissolved into solution is now going to come out of solution. So here comes a Cl minus, here comes an Na plus, and they're going to come back in and reform solid NaCl. So at this point, the rate of precipitation, the rate of Na plus and Cl minus coming out of solution, becoming a solid, is going to be equal to the rate of NaCl dissolving and becoming Na plus and Cl minus. The rate of precipitation is equal to the rate of dissolving. So what's interesting is at this equilibrium point, I know, or I have the maximum number of Cl and Na minus, or Na plus Cl minus ions in solution. And I can take the concentration of the Na plus and Cl minus ions at the equilibrium and use that to find the KSP. So at equilibrium, the concentration of Na plus and Cl minus is going to be my solubility product constant. It is the amount of ions, or it's the, let's say, the product of the concentration of ions that I like to have in solution at equilibrium. Now, so what this is it is just the molarity of the sodium ions times the molarity of the Cl ions. So these are represented in moles per liter. So now let's talk about the solubility. So let's say if I find out that at the equilibrium, I like to have 0.01 moles per liter of the Na plus ion and the Cl minus ion. So 0.1 times 0.1 is equal to KSP, and that is going to equal 0.01. So if I have 0.1 moles of both the Na plus ion and Cl minus ion, my KSP would be 0.01. Now what happens if I find out that my solution can only handle 1/10 as much? So I can only have 0.01 moles per liter of the Na plus and 0.01 moles per liter of the Cl minus. Well, in that case, my solubility, or my KSP value, is 0.0001. So at this point, what does that mean? It means that my KSP my KSP value is going to be higher So what does that mean? It means that a higher KSP value equals a higher solubility. That should make sense. Here, where we're at a lower KSP value, I can only have 1/10 the concentration as I could here, where my KSP value was a lot higher. So that is the KSP. The KSP is just the product of the ion concentrations dissolved in solution at equilibrium. If you can understand that sentence, you have got KSP under your belt. So what is QSP? Well, QSP is just like the KSP in terms of that it's going to be the product of the ion concentrations, but it is not the product of ion concentrations at equilibrium. It is just at some given point of time, doesn't matter what time. So when I first introduced this NaCl into solution, I didn't have any dissolved ions. So there, my QSP was 0. Now, just to show you real fast, the QSP, the solubility product of the concentration of ions in solution of a dissolving ionic solid. So I can compare at any given time my QSP to my KSP. QSP is how many are currently in solution at this moment in time. QSP is always going to be at equilibrium, how much do I like to have? So let's say I have a QSP or a KSP value of 0.0001. And that means for NaCl, I had a concentration of Na and Cl of 0.01 for each. So great. Now let's say I have a QSP. Nice. No, I'm kidding, it's all right. So now let's say I have a QSP of 0.000001, or 1 times 10 to the power of -6. So what does that mean? It's still the product of my ion concentrations. So for this, and I'll just write Na plus Cl minus, just so we all know, make it a little bit more straightforward. This would mean that my concentration of both, if they are equivalent, would be 1 times 10 to the -3 each. And so I don't have as concentrated a solution of NaCl at this point in time. Now, because I don't have a concentration that is at the same KSP, I'm lower than the KSP, it means I could dissolve more of my solid. Because once I hit a KSP of 0.0001, I would be at the equilibrium point. If I try to put more ions in, that would give a higher KSP value or a higher QSP. I would now be precipitating. KSP is equilibrium. As I dissolve more and more of my ionic solid, I'm going to get closer and closer to that KSP value. And I can just keep dissolving basically until I get to that KSP. But if I go higher than the KSP, well, now I'm not at equilibrium anymore. I've got too many ions. So my KSP, which is my equilibrium, is going to cause my QSP to come back down. And it's going to come back down by precipitating NaCl back into the solid form. So that is the KSP and QSP. To summarize this, if my QSP is less than my KSP, what's going to happen? My solid will continue to dissolve. What if my QSP is equal to the KSP? Well, that means the number of ions that are dissolved in solution is perfect. It's the exact amount I want to be at for equilibrium. So what's going to happen? My rate of precipitation is going to be equal to rate of dissolving, or a rate of dissociation. So that's just because I'm at equilibrium. I'm not trying to change anything now. If I go too high and I have too many dissolved, I'm going to precipitate some out. If I go below and I have too little dissolved, I'm going to dissolve more. Last scenario, QSP is greater than KSP. Now I have too many dissolved. Now I will have precipitation of ions back into solid. Great. Oh, wow. Whoops. Well, take this information and just, no, it's out of order. It's all right. Just give me, how did I take the G and not the N? Sometimes you just don't know. Huh? Well, you could have definitely written it all by now. Let's just say that's good. We'll just leave it there. We'll fix it in post. So, my editor will fix it in post. So, if you took anything away from that, just take this away. The larger the KSP value, the more soluble the solute is, and but also know those 3 points. What happens when QSP is greater than KSP, QSP is less than, QSP equals KSP. Whew. Took a lot out of me. Now,